Hello everyone, welcome to this video. My name is Amir Sinahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to make evapotranspiration map for your study area and how to calculate crop water stress index. Go to the Earth Engine code editor environment. Open your browser first and write code.earthengine.google.com. If you have account in the Earth Engine platform, you will directly go to the Earth Engine code editor environment. So, first of all, we need to identify the region of the interest. In the previous videos, I showed you how we can set the region of the interest through the drawing tools available here. But in this tutorial, I'm gonna show you how you can set your study area through the available basin layers in the Google Earth Engine data catalog. So, through the search places and dataset, type hydroshed. Hydroshed, basins level available for all around the world. And most of the time, I'm using level number 5. But you should know that the lower level number covering larger area and higher level number covering a smaller area with more detail. So I select a mid-level basin level here, and then through the map.add layer, you can see the basins for our existing basins in level number 5 for all around the world. As we are going to work with evapotranspiration layer, it is necessary to select a region including croplands, because most of the time we use evapotranspiration for the water consumption or evapotranspiration estimation for the croplands region and for the vegetation covering the farmlands. So accordingly, I want to select a part of a region in the northwest of Iran, Urmia Basin, that is including that is including farmland or croplands here. So if you want to select your desired or your target basins here, it's very easy to select that basin through a pin or through a geometry tool available here. I want to first select my own basin through the geometry tools available here, and then through the filter bones you can clip all the basin based on your study area, or you can select only the basins that is correspond to the geometry you selected. Make a new variable as region of the interest, ROI equals to get table and filter bound. Using filter bounds, we can select the shapefile basin that is correspond to the geometry layer that we already added into map. So then through the map.add layer, you will see the ROI that you selected. Oh, something is wrong. That filter bounds according to the geometry. Sorry, it was my mistake. Run the code again, and now you will see the basin covering my geometry. So in the next step, I want to have focus on my study area through the map.center object. According to the ROI, whenever code runs, I want to see my study area and also the layer through the map.center object and map.add layer. In the next step, I want to call MODIS evapotranspiration product. So let me make a new title for this part. This part is called MODIS ET product equals to, through the searches here, just write some keywords, MODIS and evapotranspiration. Over the last years, ready-to-use products such as evapotranspiration released by the agencies or organizations such as NASA and European Space Agencies that helping users to have focus on information extraction and helping on and also such kind of products motivate users to use this product in the modeling approaches. That is very helpful for extracting complicated information in the models. So, and you don't need to spend your time to calculate evapotranspiration. And now ET is available, helping you to use it for further applications such as water consumption, water scarcity, and so on. And in this tutorial, I will show you how we can use ET for the crop water stress index. It's very helpful. So first, I want to show you how we can make ET maps for different seasons. Just here, we need to use TerraNet evapotranspiration gap filled 8 days global with 500 meter spatial resolution. Import it into the code and you will see the image collection imported here, and then make a new variable as modis equals to image collection for a period of time through dot filter date, making two new variables, time start and time end, that's defining the starting date and ending date. So time start equals to, for example, I want to use all available ET products since 2001 to 2024. Time start and time end. Time start 2001, time end 2024, as you will see here. So in the next step, I need to print modis variable to see how many ET products available during this time span. Run the code. In the right panel, you will see over 1000 ET products available for this period, and in each date there are 5 bands that one of them is ET and one of them is potential ET. If you need some information about the bands, you can go to the data description here and then through the bands. Each band names and description is available with a scale factor. Remember to apply a scale factor for the visualization and getting exports. And as you can see, this product is available since the January of 2000, and also it's very valuable product for the evapotranspiration monitoring and estimation for your croplands. So now I want to use ET and potential ET with a scale factor should be considered for the evapotranspiration mapping and crop water stress index mapping. Accordingly, .select helping us to only select target bands. The first is evapotranspiration, total evapotranspiration, and potential evapotranspiration. Select that here. So in the next part, I want to show you how we can get the average ET map for the entire basin. So make a new title, average, or we can make a new part as ET mapping. So make a new variable, ET average or ET mean equals to, so get all evapotranspiration from modis variable through .select, get all ET bands from all images under modis image collection, and then calculate the average of ET per pixel. And finally, in order to have ET in a correct range of values, we need to multiply it to the scale factor 0.1. So finally, to visualize the result, map.add layer helping us. ET average or ET mean, clip it based on the region of the interest or ROI, and leave the visualization parameter empty, and its name should be ET mean in the layer setting, and use the false that preventing automatic uploading final result because it reduces the speed of processing. Save your code and run it again. turn the geometry off or remove the geometry from a display, and now we have a layer and ET average. Check it on, and we are waiting until the ET average shown in the display. So you can see it is in visualization process, but speed of processing is low because more than 1000 images involved in the processing. There are some no data values in the image that correspond to the water bodies. As you should note that evapotranspiration only calculated for the croplands and vegetations, and also we can't calculate evapotranspiration for the water areas. Typically for the water areas we only have evaporation, not evapotranspiration. So to visualize it clearer, you can increase the contrast through the enhancement tools available here. For example, through the 90% enhancement and apply, you will see the evapotranspiration, the average evapotranspiration for this region. This is a grayscale image showing and ranges from 0 to, for example, 10 millimeter, that's showing the amount of evapotranspiration per pixel. Higher values, brighter region, or higher values showing higher evapotranspiration, and vice versa. As you can see, the white spots here all corresponds to agricultural area, because in these regions we have vegetation cover, and as you can see, the rate of evapotranspiration in this region higher than the rest of areas we have in this tutorial. If you want to export this image, it's very simple to use export.image. Get export image to drive, helping us to get the final result, to download the final result from Earth Engine and use it in the desktop software. There are some arguments for export.image. The first is the image, the target image that we want to download it. The target image is ET average, and the name of output in the description equals to ET average for your study area, and also the region of the interest equals to ROI, and then a scale of output or a spatial resolution or pixel size for output should be 500 meter according to the spatial resolution, and CRS coordinate system. If you want to have coordinate system of original data, write ET average through .getinfo.crs. Through .crs you can get coordinate system from information of this data, and the region ET mean, and if you want to clip the ET average based on the layer, you need to write .clip.roi for this region. So, and the maximum pixel for each image should be equal to 1E13, and if you want, you can make a new folder in the Google Drive to save the final result. Or the folder, for example, could be evapotranspiration. So, save your code and run it again. In the right panel, in the task, you will see we have ET average, run it, and click on run again. And after a few seconds, the process of saving is over, and after the tab's color turned to blue, meaning that the process of storing into the Google Drive is completed, and then you can pick it up from the Google Drive and open it up in your own desktop software for the further programming. So now I want to show you how we can get the average evapotranspiration only for the summertime, or only for the springtime, or only for the winter time. It's very simple technique. So I want to repeat the ET mapping process, but this time I want to only have evapotranspiration for one single month, or 3 months, or a season. It's very simple technique. For example, here write ET average or ET mean for example, July, the month number 7. Oh, sorry. So ET average July equals to get from all MODIS data available. Using dot filter, we can call Earth Engine dot filter dot calendar range. Calendar range helping us to call the image collections only for a specific month, or a specific day, or a specific year, and also it's very helpful. So the calendar range arguments are start, end, and field. For example, I want to call ET values for the July, only for the July since 2000 to 2024. The start month should be equal to 7, because July is the month number 7. So the end should be same, and the field should be months. So now if you print ET mean July, in the right panel you will see that 92 elements available only for the July. You can see that all of them available for the July, and it's very helpful technique to filter your data according to the specific month, or according to the specific period of time. Or we can extend the period of the start and end date here. For example, we can get from June, July, and August, from month number 6 to month number 8. June, July, and August. You can see that in the summertime. You can see we call all the images, or all ET products, only for the summertime. So in the next step, we need to get an average for this period of time. But before that, I need to select only total evapotranspiration bands, because 2 bands available per each date, and we only need the actual evapotranspiration band here. And after then, using dot mean, you will get the average of evapotranspiration per pixel for the 20 years that is coming from only for the, for example, summertime, or the months number 6, 7, and 8. So finally, to visualize the final result, map.addLayer will help us. So map.addLayer, this time ET average for July, but now it is only for summer. Copy and paste it again. Clip it based on the ROI, ET for summer, and save the code and run it again. So here you can see ET summer is available here, and there is no problem in there is no issues and problem in the console. And using 90% contrast, 90% stretching, you can see the ET values, the average of ET values for the summertime produced, and you will see the variations. And also remember to apply the scale factor. To apply the scale factor, throw the multiply 0.1. Yes, there is. It's very simple technique. It's very simple and also very helpful. If you go to the docs, calendar range information is also available. Through the calendar range information, you will see that you can filter your data based on year, month, hour, because some of the data have higher temporal frequency for 30 minutes or hourly data. Some of the climatological products provided higher temporal frequency, and maybe you need to only filter data according to a single hour or single minute or day of a year or day of a month. And also this calendar range function is very helpful to filter your data based on these characteristics for regarding to the temporal frequency of data and producing the desired map based on. So back to the programming steps. So now you saw that how we can make ET map for our study area through the averaging technique and also the calendar range. Now in the next step, I want to show you how we can calculate CWSI, crop water stress index. So let me to make a new part into the code, and now we want to talk about crop water stress index. Variety of crop water stress index are available on the net and with different types of calculation, but one of the most popular CWSI index calculated based on evapotranspiration and potential evapotranspiration relationship. So an equation is like that. The CWSI equation equals to 1 minus 2 division between ET and potential ET. It's very simple, and if you know the basic technique in the Earth engine, it's very easy to calculate the relationship between ET and potential ET, because in the MODIS product, total evapotranspiration and potential evapotranspiration both are available here. So now I want to make a new variable with the name as CWSI equals to get all MODIS data. As you can see previously, we called MODIS data under MODIS collection, that's including ET and potential ET for 2001 to 2024. Now, as you can see, I get all MODIS data for this period, and then through .map make a new function, and in each input image is considered as an IMG here, and now we can calculate the equation for each available images. Make a new variable equation equals to get each existing image under image collection, and then through the dot expression write the equation very easily. So the equation is like that: 1 minus, in the parentheses we will have the division between ET and potential ET. So now we have two unknown variable ET and PET that we need to identify that they are related to which real variable in our code. The ET equals to each input image. From each input image we have ET bands, and PET equals to select from each input image potential ET. It's very simple. So now the equation is completed, and code returning the equation. Through the dot copy properties, the property of input images copy to the output. The output is the CWSI equation. From input images, we need to copy the important characteristic for the time series analysis. The first is the time start, and the next is system time end here. System time start and system time end, and you can rename its band to CWSI So using print, you will see how many CWSI calculated for this period. In the right panel, for the same number of images, we will have one image per date that it is a CWSI, but we need to apply the scale factor on ET and potential ET here that is missed before, 0.1, and next dot select again dot multiply for potential ET the same scale factor we have. Save the code and run it again. The image is under calculation. For each date we have CWSI image, and now in the final step I want to show you how we can visualize the average crop water stress index in the CWS using CWSI image. It's very simple, same as previous codes we have written for the evapotranspiration products, and now we can repeat the same process, this time for the CWSI. But this time for the CWSI. So CW crop water stress index, or CWSI, I want to produce an average map for my study area. CWSI average equals to get CWSI images and calculate the average. No need to apply any scale factors because it is calculated through the equation, and then through the map.add layer you can visualize it. It's very simple and without any complexity. CWSI mean, and finally we will have false, but remember to clip it based on the region of the interest and run the code again. Zooming into your study area, CWSI average is available. It is uploading, as you can see here. Unfortunately, it's a little time consuming because high number of images involved into the processing. Usually CWSI ranges from 0 to 1, and higher values showing a higher water stress index and lower values showing no stress index, no stress condition in the vegetation cover. Sorry for the issue in my speaking. So, and now in the final image, it's very hard to see the cropland region through the enhancement tools available here. We can increase the contrast because CWSI is only suitable for the croplands region, and CWSI value, it's not important their value for the water and also for the rest of the region, and only cropland is matter here. You can also remove all non-crops or non-vegetation pixels, non-vegetated pixels here through the modest land cover products. It's very easy to use. It's very simple thing. Just call modest land cover product. I want to remove all land covers except the vegetation cover and cropland. Specifically, cropland is my target for this study. So here, as I mentioned earlier in the previous videos, you can see modest land cover annually with 500 meter spatial resolution is available here, and imported into the code. It is image collection number 2. And now make a new variable. Now we want to mask out all land covers. So masking process, it's better. So make a new variable for the land cover equals to image collection number 2. If you go to the data description into the bands, you will see that the different land cover types available with annual frequency since 2001 to 2024, and typically we use LC type number 1 because we only want to select one specific class and to keep and remove the rest of the to keep the target class and remove the extra classes we have in our study area. So that select LC type number 1 is my target band, and then in order to produce a general map for my study area, I want to see the most frequent classes in my region. Through that mode, I will have a single map that's showing the frequent or dominant classes in my region of the interest. So that mode is helpful here, and now we need to select those of pixels showing croplands. To know which number showing the cropland area, go to the data description. For the LC type number 1, there is a table a table that's showing information about the values and their descriptions and also the classes. So as you can see, class number, for example, class number 14 or class number 12 is the main class for the croplands region. And we need to select class number 12 first, back to the code, and then make a new variable as crop lc dot equals. Through dot equal, I want to select those of pixels having value number 12. Through the map.add layer, we can test if cropland regions selected correctly or not. Crop.clip based on the region of the interest. The region of the interest is here. My region of interest is ROI, and leave the visualization empty and write the crop layer as name and use the false at the end. Finally, you will have a map that's showing croplands with a white color, and the rest of land covers showing with value number 0 or unknown values. So using the binary image that is created, we can mask the rest of classes from the CWSI mean. So it's very simple. Just write CWSI for crop equals to get CWSI average, that's mean, dot update mask to get update mask according to the crop region. So through the map.add layer again, we will have CWSI for croplands, clip it based on the region, run the code again, we are waiting to see the final result. If you had any problem regarding this tutorial, you can put your comments in my YouTube page below the video description, and also its code is also available in the description part, and you can compare your own code with mine. And if your problem if the problem still exists, you can contact me or reaching me out through the my YouTube page. Put your comment, ask your question, I will try to help. So now you can see that CWSI is visualizing only for the cropland region, and using this output we can compare CWSI values only for the croplands. because this index is specifically used for the cropland regions. With 90% increase, increase the contrast in the image to see the relative changes better. Now you can see that in the regions with higher values or brighter pixel or pixels with a white color, we understand that in such regions we have higher crop water stress, and also but in the darker regions there is lower crop water stress. But this is an average map, and also according to the 20 years averaging process, we understand that crop water stress mostly occurred in the downstream regions. For example, these regions with the higher values showing higher crop water stress compared to the darker regions in the upstreams. So, and using the same technique, for example, I have already shown you through the calendar range, you can calculate or have CWSI only for a specific period of months or only for a specific season. And also through the export.image to drive, you can get export from the final images or CWSI that is updated based on the cropland region. And I hope you like this tutorial as much as I do, and you can reach me out through my YouTube page, and please follow and like the videos, and I will be appreciative if you share this tutorial with the other users in all around the world, because we want to show the Google Earth Engine capabilities by such kind of tutorials and helping the users to be able to do their processing through this useful platform in the earth science. Thank you for watching us.